All right, in the last video, we looked at, actually it's a series of videos it took us to prove the angle-angle triangle similarity theorem, which basically says that if you have two triangles and you have two pair of corresponding angles that are congruent, then the triangles have to be similar. Now we can use that to prove a lot of other things. One of the things that we can prove is this proposition right here. Given a triangle ABC with B prime between A and B and C prime between A and C, then the corresponding lengths are proportional here. A prime B prime over AB equals A prime C prime over AC. If and only if B prime C prime line segment is parallel to line segment BC. And in this case, triangle ABC is similar to triangle A prime B prime C prime. Half of that is a direct corollary of this angle-angle triangle similarity theorem. In other words, a corollary is a theorem or proposition that is a direct result of an earlier result, an earlier proposition. So in this case, you'll be able to just get a couple of angles congruent and then just immediately get the result that you want of the similar triangles in one direction. Then you have to prove it in the other direction. I'm going to leave that one as a homework task and not go over the proof right now. So the question also that I want to talk about in this video is just setting up something here that we're going to be looking at for a couple of videos now and a couple of little pieces in this the text here. So recall that we spent a few weeks considering what are some minimal set of conditions which are sufficient to determine that two triangles, or a triangle with itself, are congruent. For Euclidean geometry, we concluded that SAS, ASA, AAS, and SSS conditions were sufficient, but AAA and SSA conditions were not. Thus, we have the SAS postulate, and then the ASA, AAS, and SSS triangle congruence theorems in Euclidean geometry. So in the homework task, we will try to determine if there are other corresponding similarity criteria for triangles. Actually, we're going to do that in the next few videos. And so remember, all the similarity discussions here are just Euclidean geometry only. Now, we've already determined that knowing two corresponding pairs of interior angles are congruent is sufficient to determine the two triangles are similar, the angle-angle similarity theorem. In order to have a set of proportional side lengths, this must involve at least two sides. So what if we only given one pair of corresponding congruent angles and a pair of proportional side lengths? That would be sort of, we might call the SSA or the SAS proportionality situations, depending on whether the angle is opposite one of the sides that was included in our proportionality, or whether that would be the SSA, or the angle is included between the two sides in our proportionality condition. So, and then that's one option, okay? Um, and then the other one is, what if we are given only that the three side lengths are proportional? We know nothing about the angles. That would be the SSS proportionality situation. So notice that the SSA, SAS, and SSS conditions are slightly different than the SSA, SAS, and SSS congruence conditions. In the congruence conditions, an S indicates a pair of corresponding congruent sides. In the similarity conditions, SS or SSS indicates two or three sides that are proportional. That is, the ratio of corresponding sides is a constant. Okay, can you see why this would not make sense with only one S? You can't have a pair of sides proportional to any. I mean, there's nothing to be equal to. It's just one fraction. You have to have two fractions to make them equal. So therefore, there's no corresponding ASA or AAS similarity condition to consider. And actually, these would give us the AA condition anyway, which is really enough to determine the triangles are similar. So notice that other than the AA similarity condition, which we already know is sufficient to make the triangle similar, all other similarity conditions must include two or three sides, since we have the ratios of 2 or 3 corresponding sides to be equal in order to have at least one pair of proportional sides. The only condition left to check are the SSA, SAS, and SSS similarity conditions. So first of all, let's think about the SSA similarity condition. If we just think about this a little bit, we realize we already know the answer to this question. We are given a correspondence between two triangles with two of the sides having proportional lengths, and the corresponding angles opposite one of the sides are congruent. That is, say A prime over AB equals A prime B prime over AB equals A prime C prime divided by AC, and angle B is congruent to angle B prime. Is this enough to conclude that triangle ABC is similar to triangle A prime B prime C prime? Now, I'd like you to think about that just a minute before we go on, and I think you already know the answer to this one if you think about it just a little bit, without doing any special investigations other than what we've already done. Press pause and come back when you thought about it. Well, if you thought about it a little bit, I think we already know the answer is no. We already know that the SAS similarity condition is not sufficient to include the triangles are similar because the SSA congruence condition doesn't work. And let me see what I mean by that. So we know there are examples where the SSA congruence condition is met. So like A prime B prime over AB equals A prime C prime over AC equals 1. So they're proportional with 1. In other words, A prime B prime equals AB. We've got corresponding congruent sides there. And angle B is congruent to angle B. So it meets the SSS congruence condition. Okay. And that definitely meets the SSA similarity condition. But the two triangles could be non-congruent. We have examples of that, what we call the ambiguous case. So any pair of triangles from the SSA ambiguous case that we studied earlier would serve as a counterexample, such as this pair here. So in this pair down here, triangle ABC and ABC2 have a common angle here. These side is congruent to itself. This one and this one are congruent, so it meets this proportionality setup and this here, and yet those triangles definitely are not similar to each other. All the other angles, for example, this angle at C2 and this one at C are different. The two different angles at B are different, and the sides are not proportional down here. So it doesn't meet any of the other things. So we can strike out SSA as a possibility. Just throw that one away, just like we kind of did for congruent triangles. So then that leaves us these two situations here. SAS and SSS. So SAS would be this. We are given a correspondence between two triangles with two of the sides having proportional lengths, and the corresponding included angles are incongruent. So that is A prime B prime, that distance, divided by the distance from A to B, is equal to A prime C prime over AC, and angle A is congruent to angle A prime. Is this enough to conclude that triangle ABC is similar to triangle A prime B prime C prime? That's our SAS question, right? At this point, it's a question mark. How about the SSS similarity condition? Is that enough to make the triangle similar? That is, we're given a correspondence between two triangles with all three corresponding sides have proportional lengths. That is, A prime B prime over AB equals A prime C prime over AC, and that's also equal to B prime C prime over BC. Is this enough to conclude that the triangles are similar? That is it enough to conclude that all the corresponding angles are congruent as well? So I'm going to give you some tasks to try to do on your own and see if you can determine if these are going to work or not. So this is a task in Euclidean geometry with a GeoGebra exploration. So in GeoGebra, construct a proper angle slider and input box for an angle measure, say alpha, and a positive number slider, a corresponding input box for a dilation factor K, and for now we'll just do it between 0 and 1. It could actually, you could make it bigger if you want. This just needs to be bigger than 0. Construct a triangle ABC and a triangle A prime B prime C prime so that the measure of angle A equals the measure of angle A prime, and that's the measure given by the angle slider. Make A prime B prime K times AB and A prime C prime be K times AC, And this should be just two separate triangles, not sharing any parts or any points necessarily. Then compute the measure of B prime C prime over BC. Compute that and see if it's the same as this factor K. Okay, and then measure the remaining angles and see if their corresponding ones are congruent. So what do you notice? If you think it's just test it out by manipulating the sliders and the vertices, and if it always works, then we're going to probably assume that the SAS similarity thing works. If not, you should come across a counterexample and you prove it's false. So I'm going to leave that for a task for you to do on your own. If you want to pause and come back after you've done that, that's fine. Or let me just give you another task too, because here is and here is a hint. Okay, so we're trying to see if the two triangles are similar or not, and then we're going to test our conjecture by manipulating the vertices and sliders, and then prove or disprove that the triangles are similar. All right, so the second one is to basically do the same thing for the SSS similarity condition to find out if that's enough. So in this one, construct a positive number slider and input box for a dilation factor K. Construct just a general triangle ABC. And another triangle A prime, B prime, C prime, so that you get A prime, B prime is K times AB, A prime, C is K times AC, and B prime, C prime is K times BC. You're going to have to probably use uh, circles by a certain radius. Okay, and then you'll have the sides proportional then with proportionality constant K. So then measure the remaining angles, and what do you notice? Are the two triangles similar? Test out your conjecture by manipulating the vertices and sliders, and once again prove or disprove the triangles are similar. Okay, let me give you a hint. The key to the proofs of both of these things is to construct a triangle inside the larger of the two triangles so it's congruent to the smaller original triangle and similar to the larger original triangle. You'll need to make use of the Euclidean parallel postulate as an early step, so you're going to have to be constructing a parallel line at some point. And the construction is basically the same in the proofs of both of them, but the reasons justifying why it produces desired results are a little different given the two different hypotheses. And both these theorems make use of a triangle congruence postulator theorem, and they use the AA triangle similarity theorem. So those are some of the key pieces that you need to see if you can assemble to do these proofs. So I'm going to leave this video there. See if you can try these tasks on your own and see if you can make up do these proofs on your own. Please try to do that before you move on to the next video.